Hello, my name is Jacek Bandik. I am product owner at dSPACE, and today I want to show you how to set up a software-in-the-loop simulation and development environment. This learning connection is mainly intended for C code developers who need to integrate an existing plant model for experimentation, testing, and debugging. Here's the agenda. In the first part, I will use slides to describe the use case covered in this learning connection, the accompanying challenges and problems, and my solutions for these. The new V-ECU SDK plays a major role here, so I will describe it in more detail. And after that, the biggest part will be a hands-on demo where I show how to set up and use the SDK and VEOS based on an example project. Finally, I will end this video with a summary. So, this is your problem. You have an existing plant model. In this case, a SIG file created with Simulink. There's your code you want to test and develop. And the challenges you have to overcome is to connect both. You have to execute both in a synchronized manner. And you want to be able to attach a debugger, well, so you can inspect and debug your code. So my solution to this problem is a setup with the dSPACE VEOS simulator. In order to do this, you have to wrap this code in a so-called virtual ECU. That's an artifact that can be executed by VEOS. So the main challenge to overcome is to wrap your code into it. And for this, we have provided the newly released V-ECU SDK. This is a lightweight tooling set, completely command line based, which you can integrate into your familiar IDE. So what happens is that the existing C code somehow has to be glued into the virtual ECU. You also have to define the communication ports. This all can be done with the help of the virtual ECU from inside your IDE. It's completely text-based. The resulting artifacts can then be added into a VEOS simulation. They can be connected in VEOS. And what you can do is then to start the simulation again from your familiar IDE and to debug your code. Some key takeaways of this setup. One of the big advantages of VEOS is that it is fully time synchronized. What does it mean? It means that if you set a breakpoint in your code here, and the breakpoint is hit, then the whole simulation is stopped. So also the execution of the SIG container is stopped here. And if you continue the execution from your IDE, then the complete simulation also continues. VEOS utilizes what is called virtual time. So the time passing in this simulation is not bound to real time, but basically can run as fast as your hardware allows it. And this is also the second big benefit of this setup, because you don't have to actually wait the real time to occur, but you can speed up the simulation. And so, for example, your breakpoints will be hit much more early. Okay, before I start the hands-on part of this video, I wanted to say a few words about the V-ECU generation until now. So the V-ECU SDK is quite young toolset. We released this in the summer of 2022. It's free for download for all VEOS users. And it addresses exactly this case in which you have rather a quite simple code, or probably consists of a single step function, which you want to wrap into a virtual ECU. Before the V-ECU SDK, the main tool for V-ECU creation was SystemDesk. It was intended for complex, full-blown AutoSAR ECUs or for complex code-based ECUs, which is also the main advantage of SystemDesk. You have all the proper tooling for this, but this is also the main disadvantage. It's quite complicated to create full-blown AutoSAR ECUs. As I already mentioned, with the V-ECU SDK, you can stay in your IDE and you can stay as close to your code as possible. Okay, enough slides for this introduction. Let's start with the hands-on part. First thing to do is to download the V-ECU SDK. You can find it on the dSPACE homepage. If you search for the V-ECU SDK, it's just the first hit on the top. You would have to log on with your dSPACE account, and then you are able to download the SDK. I've already done this, and if you extract the main file, you have basically three resulting files: the SDK itself, the demo project, which I will use for this presentation, and the manual. I highly recommend to read the manual, actually. It contains all the necessary steps for the setup of the SDK, how to configure the YAML file we will see later, and it also contains the example here, so you will be able to do the steps here with the help of the manual, also for yourself. Okay, so I've already extracted the contents of this zip files. Here's the location of the SDK. What I recommend to do is to register it in the environment path variable. I can do this in the system settings. For example, for myself as user, where I add the V-ECU SDK. Okay. This ensures that when I call the command line tools, I can call them from anywhere. And then I continue to have a look inside the example project. I open it in the Visual Studio. It's by the way, it's called Lunar Lander. It contains a very simplistic algorithm for landing the lunar lander, which basically takes in the height from the plant model and puts out the fuel rate into the plant model, and so tests if the lander properly decelerates. So basically I have one method I want to test. This is a tire autopilot. And now the interesting thing is when it comes to the virtual ECU, how to convert and include this into a virtual ECU. And for this, I create basically these two artifacts. One is a YAML file. This is, a text-based configuration file that helps me to define necessary information for the V-ECU creation. I will just black out all contents as I want to fill in them from scratch, just like you will have to do with your own project. And another task to do is to write down the glue code that connects the environment, simulation environment from VEOS to your code. I also blank this out as so I can write this down from scratch the same way you will have to with your project. Okay. So, how to write this glue code? In most cases, you will want to write some kind of a single step function. So let's call it step. And in most cases, it will consist of the parts read inputs, execute algorithm, and write inputs. So, what will be the inputs and outputs? In my case, what I'm interested in is here the fuel rate and the height. I want to read in the height and let my algorithm calculate the fuel rate and write it out. And my controlling algorithm is the autopilot. So what I have to do is I have to define my inputs and outputs in the YAML file. We try to keep the syntax and the contents of this file as simple as possible. By the way, everything is also described in the manual. So when you're starting and you have problems to type the first proper keywords, just have a look into the manual. So I already mentioned I have one input and one output. Inputs just called height, and the output is called fuel rate. Okay. To give you a bit more background information about what I have just done here. This YAML file, which by the way is located in the same folder as my glue code. This YAML file is read by the V-ECU SDK tools as you execute them from some folder in the command line. So if I would execute a V-ECU command here, it will automatically look into the autopilot demo folder, take the first YAML file as configuration, and do whatever is configured in this file. And what I've just done right now, I've defined height and fuel rate as input and output. And what the virtual ECU can do for me is now to generate the proper headers that glue this information into actual C methods. Another thing I want to configure before I start the actual header generation is to define a header directory, because I don't want to pollute my code file directory here, my code directory. So I define a V-ECU header dir here, headers. I save the YAML files, so when I now execute the V-ECU header, command. It generates all useful and necessary headers that represent to me the virtual environment, simulation environment, into the headers directory. What I also then do is to add this header folder into my include directories, so I have a bit less to type when I include those files. And what I can do now, for my step function, I can include the VI header. The VI header stands for Visualization Interface, and as I already mentioned a bit, it contains all useful and necessary methods and symbols to access the virtual simulation environment. Bit more complete description of the available interface is also contained in the V-ECU manual. What we need at this place is VI. Every visualization interface symbol starts with VI, and we want to read a float. I know that the data type of the symbol is float 64, so I use it. And the identifier of this input is VI in height. This was generated from me by the V-ECU header command I have just executed right now. So I can use IntelliSense to access my defined inputs and outputs. And I want to write this into the height variable. Okay. The reason I don't have IntelliSense for height here is because of course, I want to glue my actual code here, so I have to include it also. Now also the my internal variables are available here. As I have just included the autopilot headers here, I have also the autopilot function itself available for call. And now I can write out my float. And this was the VI out fuel rate, which I get from the fuel rate from my internal variable. Okay. What you can do, you can, of course, have multiple input and outputs. You would just write them underneath. And also you have advanced possibilities to define the type and the form of the inputs. If I take a brief look into the manual, what you can do, in the very most simple form, you just type in the name, and the V-ECU assumes a float 64 or double type. What you can also do is extend this information with the type. Here you would just type down the actual C type to use. For arrays and normal variables, you can also define optional init values. And an array size if you use arrays. There is also a special construct with VEOS offers you as an interface. It's basically intended for huge data. It's a so-called binary port. So the type is binary, and it allows for dynamic sizes with a much bigger size, and basically it's a byte stream you can access here. Okay. So what I've just done is to define a step function, what I want to be executed cyclically. So the next thing to define is basically a single entry method, which will be called by the VEOS simulator when the V-ECU is initially started. And in this method, I want to register this step function for the further cyclic execution. I start with kind of handler. I want to remember the notification identifier for the cyclic execution. And I write here my main entry method for the V-ECU. I call it glue code init. It's called at single time at the startup, and again I start here with VI, and what I want to is to schedule a cyclic notification. I want to have the step method executed at first time 0 seconds after execution starts. So basically at the execution start, I want to have to be executed every 0.1 seconds. And I remember the handler for it in the step notification. Xender here is not used further, but in more advanced scenarios, you would have the possibility to, for example, to stop the cyclic execution using exactly this identifier here. Okay. So with this, I'm basically done when it comes to the glue code. To wrap it up, I've got my step method, which I want to have to execute cyclically. I read the inputs, I execute my algorithm, I write the outputs, and one time at the startup of the virtual ECU, I want to register the step methods for cyclic execution. And that's my glue code. Next thing to do, well, I could just try to build it and see if I have done some errors. A little typo here. Okay. I've just compiled all my code. One side remark about the compilation. The best way to wrap your code into a virtual ECU is to compile it into a static library, which then later greatly simplifies the debugging process. So what I want to do is I want to build a static library, and I want to make sure I have the proper target selected. Okay. So what I've done here, I have used the YAML file, the configuration file for the virtual ECU SDK to generate proper virtual interface header files. I can use this generated headers here. So I have them accessible for my glue code. I've put in my actual code, and I made sure that it is called cyclically. So what I haven't done yet is to generate the actual virtual ECU and to wrap everything into a simulation. This I want to do right now. So one thing I already mentioned is I've built a lib file. So I just want to add it here. I would like to generate the OSA file. The OSA file is basically the simulation file for VEOS. I want to have this in another folder, so it does not pollute my source folder here. So I define another file target. I call it autopilot OSA. And what I also have to do, otherwise VEOS will give me warnings when importing and building this virtual ECU. I defined a build target. That's the information for VEOS, for which platform the included lib files were compiled, and in this case it's host PC32 with mass VC. Again, you find a reference in the manual of the SDK if you have problems to type in the proper keywords here. So that's all I need to define for the V-ECU and the... Oh, no, I've forgotten one thing. What we also want to specify is a startup function for the V-ECU startup. So the one-time startup function I've just written is the glue code in it. Okay. Now I've basically configured and prepared everything for the virtual ECU build and for the OSA build. And I now just can start it with V-ECU build. Again, it looks into the current YAML file and uses the information from the YAML file to build my virtual ECU and also to create the OSA file. So this is finished successfully. Next step I can do is use the VEOS player to have a look inside the created OSA file. So what I can do here, here's my VEOS project file and project VEOS simulation folder with everything necessary for execution there. And I can use the dSPACE VEOS player to have a look into this just generated OSA file. And what I see here is my virtual ECU, the autopilot, with the defined output and input signals. Again, the reason why I see this output and input signals here in the virtual ECU is because I properly defined them here in my autopilot YAML file, and the V-ECU SDK generates the necessary configuration for VEOS so it can use the signals here. Next thing to do is to add the lunar lander landing module. This is a ready-to-use SIG file, so I can just import and build it here. Okay, I see it here. It also has its in and out ports for the communication, and I can now connect the fuel rate and the height. So that's the last step to do before the simulation. I can just save the file here. And now I'm ready for execution. One thing to mention is that this connection has to be done only once, and it remains in the OSA file. Of course, until you add further communication ports to the V-ECU, then you would have to connect the new ports once again here, just one time, and then everything remains as connected. Next thing to do is to load the simulation. I will explain a little bit about why it is a simulation load and why we don't start the simulation yet. And the reason for it is that the virtual ECU will be running in a separate host process. And if you want to debug it, you need the ID, process ID, to be able to attach to it. So what I have just done right now is to bring this simulation into a loaded state where everything is prepared for execution, but the simulation is suspended before the step 0. So what I can do is to attach to this process 25640. Okay, this is a VEOS VPU host, so it looks like the proper process to attach to. And now I'm able to set breakpoints. Okay. First thing I want to check out is if the proper values are read from the height environment model signal. So I set a breakpoint before my execution, and next thing to do is to start the V-ECU. Again, you can bind this command to some key or button, so you are able to start it from your IDE. You don't have to type it every time. So what I see here is that the simulation has actually started, and the breakpoint is set. So the simulation is suspended right now, and I have also time to inspect what happens in my code. And when I look into the height variable, I see it's currently 0. Okay, that's interesting. I will have to look into this. Okay, I see nothing changed with the fuel rate, so my autopilot at least did nothing crazy. I continue the execution into the next step. So, and when I now look into the variable, I see it's at 15,000. So what just happened is, because I schedule the execution of this step method at the simulation time 0, it was basically executed in an undefined state. Because at the time 0, none of the plant model could be executed, so no meaningful height input was available for the simulation here, for the virtual ECU I'm debugging. So that's the reason, perhaps if you ask yourself why we want to schedule a cyclic notification after some time, that's exactly the reason why you in general want to postpone your first call of the step method to a time point when you know that the simulation has a defined state. Otherwise, you would have to deal in your code with this crazy value changes from the step 0 to step 1. I can build this again. And if I want to attach again to the simulation, I have to load and repeat the process of attaching. As now I have, of course, a new simulation here because I updated the OSA file. And now I take a look at the height variable, and what I see is that in the very first steps, it has a more meaningful value of 15,000, exactly as the result of my minor correction there. So, if you're still with me, I want to finish with a summary. I have shown you how to wrap your code into a virtual ECU and how to execute and debug it in a simulation, including a plant model. I have used the new V-ECU SDK for this. This is a lightweight toolset which allows you to stay in your familiar IDE and as close to your code as possible. This makes it easier for you to get started with SIL testing in VEOS while providing all the benefits of the VEOS simulation. Okay, that's all I have. Thank you for listening and have a nice day.